Welcome back. In today's video, we are going to explore Wheatstone bridge, which is used in measuring unknown resistances with high accuracy. To start, you have already learned that resistance can be measured using Ohm's law using a voltmeter and an ammeter, but this measurement may not be accurate for low resistances. This is where Wheatstone bridge comes into play. Wheatstone bridge is a precise instrument used to measure an unknown resistance by balancing the bridge using known resistances. Let's break it down. Here is a typical setup of a Wheatstone bridge. P and Q are two resistances connected in arms AB and BC. R is an adjustable known resistance. S is the unknown resistance we want to measure. As sensitive galvanometer along with the key K2 is connected across the points B and D, and a battery E with the key K1 is connected in the arm AC. When we close the keys, some current will flow through the circuit and you will see a deflection in the galvanometer. It indicates that there is some potential difference between the points B and D. Consider the following three possibilities. First is point B is at a higher potential than point D. Potential at point B is greater than potential at point D. This implies that the current flow from point B to D in this direction, and the galvanometer will show a deflection, say right. This is the first possibility. Second possibility is the potential at B is less than potential at D. Then the current will flow point D to point B in this direction. In this case, the galvanometer will deflect in opposite direction. So let's assume left direction, that is galvanometer will be in this direction, galvanometer will be in this direction. Third case is when the potential at point B and D are at same. In this case, no current will flow through the galvanometer, it will show no deflection. This is called null condition. It is in this condition the Wheatstone bridge is said to be in the state of balance. This happens only when the potential drop at the point P is equal to potential drop across the resistor R. I1P is equal to I3R. For this junction, if we apply the Kirchhoff's junction rule, I1 is equal to I2 plus Ig, because we have considered Ig to be in this direction and I2 to be in this direction. And if you apply the Kirchhoff's junction rule to this node, this is I3, this is I4, this is Ig. So I3 plus Ig is equal to I4. But we know that for the third case, Ig is 0. Then this equation can be written as I1 equal to I2 and I3 equal to I4. We also note that the potential drop across Q will be equal to potential drop across S. Then we can write this as I2Q is equal to I4S. So we have one equation here, we have one so dividing the equation, first equation by second equation, we get I1P by I2Q is equal to I3R by I4S. But I1 is equal to I2, I3 is equal to I4, I3S. So P by Q is equal to R by S. This is the condition for which a Wheatstone bridge will be balanced. We saw that the S is the unknown resistor. With this equation, we can find the unknown resistor as RQ by P. The measurement of resistance by Wheatstone bridge method has the following merits. The balance condition at null point is independent of the applied voltage V. In other words, even if you change the EMF of the cell, the balance condition will not change. The measurement of resistance does not depend on the accuracy of calibration of galvanometer. Galvanometer is used only as a null indicator. The main factor affecting the accuracy of measurement by Wheatstone bridge is its sensitivity with which the changes in the null condition can be detected. It has been found that the bridge has greatest sensitivity when the resistance in all the arms are nearly equal. Now let's see an example of Wheatstone bridge circuit. Calculate the value of R shown in the figure when there is no current in the 50 ohm resistor. So this is the Wheatstone bridge where the galvanometer has been replaced by 50 ohm resistor. The bridge is said to be balanced when there is no current in 50 ohm resistor. The condition for the Wheatstone bridge is P by Q is equal to R by S. Since P is here 20 ohm, Q is here 40 ohm, R is here 10 ohm, and S is the R. Therefore, R is equal to 10 into 40 by 20, which is equal to 20 ohm. To recap, the Wheatstone bridge works by balancing resistances. Wheatstone bridge is used to measure accurately an unknown resistance S by comparing with the known resistance P, Q, and R. In balance condition, P by Q is equal to R by S. Thanks for watching. If you found this video helpful, don't forget to like, share, and subscribe.